Okay, this is going to be an overview of what solutions are and how we can understand the calculations to get to concentration in a solution. So let's start with the basics. Solutions deal with water. Water is the base of that solution. Technically, a solution is a compound that is dissolved in water for the most part. When we say an aqueous solution, that is definitely the definition. So when we look at water, I have the Lewis structure here, and I put the oxygen in the middle, and I have some lone pairs. And if you remember at all about molecular geometry, is that we have this parent geometry of, you don't need to draw on yours right now, but I have 4 electron clouds, right? 2 bonds, 2 lone pairs, and because of that, if I was drawing this out, the locations of those electron clouds would repel each other, and I'd have a lone pair here and there, and I would have my H's, and because of that, right here is my actual structure, and it would be bent, and that is what we're kind of looking at. But initially, with those 4 clouds, it is called a tetrahedral, right? And then because of the fact that I kind of don't look at the lone pairs, the molecular geometry itself is bent. And bent is so important to have an understanding of because it's not linear. If it were linear, like this, then it would behave very differently with other molecules and other charge compounds. So we want to look at that a little differently. So if I just come back over here for a moment, we have some interesting things that we can label. So first, bond dipoles, they're called. So on the periodic table, there are elements that basically pull or hog electrons. So if I just drew a really generic periodic table here, you have to understand that to the upper right, that is where atoms, they will pull or hog electrons from other elements. So because of that, my hydrogen here would be partially positive, and that's how we would write that. That's a partial charge, because the electrons are being pulled towards that oxygen. And my oxygen would be partially negative. Well, there is an overall dipole moment, it's called, and I can make one big dipole. And again, the dipole, honestly, at the bottom of it right here, looks like it's a positive. Well, that positive tells me that this end of the water is going to be positive, and I'm not even going to rewrite that. The top part is negative. So my water is a polar compound, and that is such an important concept to have. That polarity causes that interaction between charged ions, between other polar compounds, or the lack of interaction with something that may be nonpolar or lacking a charge. Okay, so let's quickly talk about a concept that you have heard of many times called hydration. If I say hydration for you, you probably think of having to drink water. Well, that is similar, but what it is, it's ionic compounds that dissolve in water. So you just have to have an understanding of what that looks like. So whenever in chemistry you're trying to describe something, a lot of times you can describe it with a chemical formula, reactants and products. So if I took a salt like calcium nitrate, okay, and that's a solid to begin with, all right, and if I just took that and I dropped it into some water, I hope that you would look at that formula and say nitrates are soluble. So what it would do is probably break up into its ions, and I would have Ca2+, and it's 2+ because it's an alkaline metal, and I have nitrate, which is NO3-, and that's going to be AQ. And then you need to look, and I have 2 nitrates right there, so I'm going to need 2 nitrates right there. And that truly is a hydration type formula. Couple quick things just to note is that this compound on the left has no charge. So when you are trying to balance anything, you have a 2+ here and a -1 times 2. Well, 2+ and 2- equal 0. So I have 0 charge on each side. So we're going to use that concept of when a salt that is soluble, which can dissolve, is dissolved in water, I'm going to have those types of ions waiting for me. Okay, so let's talk about this at the most basic level. So if I have a beaker and I want to make a solution, okay, and let's just say I have a solid that I put in there and I am taking a snapshot. I'm going to assume that this solid eventually dissolves. Okay, it's going to break apart. But just for this one little moment, it's sitting on the bottom just for a conversation. We need to make sure we just have two very important vocab words down, is that solution has two parts. It's the liquid, which is usually water, and that is called a solvent. And then the solid that dissolves in the solvent is called a solute. Okay? Just FYI, if you would have two liquids, because that's a good question always, like, what if I have two liquids? Well, the greater volume, so if you drop two of them in together, the greater volume is the solvent. So just as an example, let's say you have 50 mils of A and you have 75 mils of B, and you plop those both into a beaker. This would be my solvent, which is B because there's more of it, and this would be considered my solute, just as a total hypothetical. Well, the big key to this is that if I have a certain amount of solute in a certain amount of solvent, then there's a ratio there, and that ratio is called a concentration. And this is so important in chemistry. So what we do is, this concentration has a very special name. We call it molarity. And that molarity is the moles of solute over the liters of the solution. And if you're thinking, well, where's the word solvent? Sometimes solution and solvent are interchangeable, but the solution sometimes is the entire volume of the solute and the solvent. So the solute, when it dissolves, there's more volume in there than just what the solvent was. There's a shortcut for this. We just make capital M, it's got to be a capital M, is mole over liter. And what I love about that is that there aren't many equations that actually have all the units as the equation. So it's molarity equals moles over liters. If you ever, and we will see this in a moment, need to do a shortcut, let's just say a solution has a 1.5 molar solution of, I don't know, of NaCl, okay? What you could say is it's, you could put a bracket, and then you could say that, like, NaCl is 1.5, or like the question could just say, what is the concentration of NaCl? When you see brackets, that means molarity. Okay, so let's see how this works. So my first example. It says calculate the molarity of a solution when 1.86 grams of HCl is dissolved in 26.8 milliliters of water. Honestly, the biggest thing for you always is to just keep in mind that we have units that we have to follow. So when I see this, milliliters, I'm thinking probably liters. When I see grams, grams can always get me to moles. So let's take this a step at a time. I have 1.86 grams of HCl, and I want to get that to moles. So hydrogen plus chlorine is approximately 36.45 grams. And I write this all out. Okay, so that's going to be 0.0428 moles. Then, what is this in liters? What is that in liters? Well, I need to divide that by 1,000. So I'm actually just going to place that right underneath there. Let's just keep the story or the narrative going right here. Now I have moles over liters. And I divide that, and I want 3 sig figs, and I'm going to explain why. If you look at your problem, you got 1, 2, 3. You got 1, 2, 3. So I should have 1, 2, 3 sig figs. And it's 1.60 molar. That's how you say that. Or 1.60 molarity. And that's how I would do that with some basic ideas of just grams and milliliters. Here's a different kind of problem. It says calculate the molarity of each ion present. So this will be new. Again, oh, I have grams and I have liters. So the liters will be done, but I do need to get to the grams. So let's do this part first. All right, and if you add up the calcium and the chlorine, it rounds to about 111. And I get 0.725 moles. I'm going to place that right over my 0.4 liters. And I get 1.81 molar of CaCl2. So that is the first part of my answer. That's not the last part. So if I had CaCl2 and I drop it into some water, okay, what's going to happen is I'm going to have Ca plus floating around and I have Cl minus floating around. And in fact, what was our hydration equation? It would look like that. So honestly, this is my beaker. Wouldn't this make more sense? That I have two chlorines floating around and only one calcium. So when I am asking what is the concentration of my final two ions, this is how I can write it. So what I need you to understand is exactly that picture right there, is that if this is 1.81 molar, that means when this comes off, that I have 1.8 molar of Ca, and I have 1.81 molar of Cl. But I have two Cls. So I have 1.81 molar of my Ca2 plus, but I have 3.62 molar of my Cl minus. Because I have two of them, they have to add up because each ion carries the same molarity from the original concentration